Welcome to our next lecture on the Internet of Things. Today we are going to conclude our discussion of IoT infrastructures by taking a closer look at application protocols. So, to recapture and revisit our networking overview, we have seen our ISO OC networking stack already with our 7 layers and the simplified view on the right-hand side of our TCP/IP network layer stack, which in general consists of a network interface, then a network layer, which handles addressing and routing, a transport layer, which handles communication between endpoints on the network, and then an application layer, which encompasses the 3 upper layers of the ISO model, so application, presentation, and session layer. And on the application layer, we have specific protocols, for example, for the web, like the HTTP protocol, for file transfers, like FTP, for remote shell access, like SSH or Telnet. So the question is, how do applications that we are going to use in the IoT actually communicate? Well, they communicate as application protocols, as to be expected, and these run on top of the transport protocols. So they are in this yellowish layer on top of the 3 lower layers of the TCP stack here. So what happens is that we have packet-oriented transport on the network, so we have data packets on the network, and as payload inside of these data packets, we have the application data, which is formatted according to a given standard. So we say that the application data is encapsulated in the data packets of the transport layer. So the transport layer takes care of, for example, creating a session, assigning port numbers, and so on. These transport layer packets are in turn encapsulated in network packets, which provide the, for example, sender and destination address. And these in turn are encapsulated, for example, in Ethernet packets, which provide additional information like a checksum and like some local network addresses to identify a station on the local network. So when we want to build applications for the IoT, it's highly important that these applications are able to communicate, even though they might be written by different companies, might be provided by different vendors, running in different applications on completely different devices, because otherwise an Internet of Things won't make too much sense, because without communication, you will just have standalone systems. So the question that comes up is, should actually every application try to define its own protocol? Well, this has some problems which are probably relatively obvious. If each application tries to define its own protocol, we'll end up with lots of incompatible products. We'll end up with products where we have real difficulties enabling interoperability. So if we buy, for example, a couple of sensors from vendor A, another couple of sensors from vendor B, and devices to be controlled like lamps or whatever you can imagine, heating systems in your building from vendor C. If none of these would talk or use a common protocol, then we need adapters and translations to enable them to talk to each other. So to enable the sensors, like an occupancy sensor or a temperature sensor, to actually effectively control a heating or a light in a building. So what we want is something that makes interoperability easier, and a common standard for this might be really useful. And this then also avoids that we have to reinvent the wheel for every device, so we don't have to implement critical features, for example, for security, because this should be left to security experts, because application experts can concentrate on the application and not inadvertently introduce security problems, because they also have to add security to each and every product they develop from scratch. So the solution we want to use here is what is commonly called a middleware. So a middleware, as the name implies, is something that sits between the operating system, that sits on top of the hardware, so as the basic layer of software, and also between the operating system and the application on top. So it's a mediator between what happens in the operating system and on the hardware level. and what the application requests as services. So middleware is a software that provides services to applications beyond the services that are provided by the operating system. So we don't have to care about the operating system, no matter which operating system we're going to use on an IoT node. If we use the same middleware and maybe the same TCP/IP protocols, obviously, on these machines, they will be able to communicate with each other. So our middleware for IoT should provide common communication protocols, common data formats, and possibly also a joint programming interface for our IoT application. And this is very useful because it helps to reduce the code size for applications. So if we have multiple IoT applications running on one node, they can all make use of the same library of middleware components, for example. So we only have to have one copy. And if we have one copy, we don't have to care about version differences between different versions of libraries, for example. And in turn, this reduces bugs because a commonly used middleware library is going to be used or is going to be tested more thoroughly, is probably going to have fewer bugs than if you would derive something and write something from scratch for each of your applications. So middleware for the IoT poses two challenges for us. Challenge number one is we should be able to build some generic middleware approach that is able to support the requirements of a large set of applications run on a large set of different hardware and operating system software configurations, and also to support different networks, for example, but still should be resource efficient. So it shouldn't be a monster of a library that's slow and big, but still small and nice. So we have these competing requirements of being very universal, but still very small and efficient. And there is a second challenge. We want one interoperability standard. So obviously, when you develop systems, there are different approaches to do this. So obviously, like in many other systems, like in hardware, we have different processes. In operating systems, we have different operating systems. And of course, in middleware, we have different standards for protocols, for middlewares, for APIs, for communication. So we have more than one middleware standard. And the problem is, how can we get these to talk to each other? So how do we model communication in an IoT system on a high level? So the basic idea is the one we've already seen in TCP/IP networks. We want to send and receive something. So in TCP/IP networks, this information is encapsulated in packets. These packets contain address information, port information, and then something very generic, which we call a payload. And this payload is just a stream or a set of bytes, which can have any values. So the idea is really to use this payload to structure it and then to define what we call messages. So inside of such a TCP/IP packet, we send a message. And a message is just defined as some certain defined amount of information, which is exchanged between a sender and one or more recipients or receivers. And the important thing is that these messages have a standard that the sender and the receivers have agreed upon. So a message consists of several parts. A message has a header or several headers. So headers are supplemental data which are placed usually at the beginning of a message. This could be an addressing information, or as we can see later on, a topic of a message. So we can categorize messages according to different topics. We might have metadata in a message. So metadata is data about data. So for example, this could indicate this is a certain message type. So this is a request or a reply, or it could also contain something like a checksum for fault tolerance. So you can check if the message that's received has not suffered any corruption on the way from sender to receiver. And of course, finally, we have something again, which we call payload. So it's recursive and put into each other again. So the payload of a message is just a part of transmitted data that is the actual message we want to transfer. So when we want to exchange messages, there are essentially two ways. One way is very analogous to when you do a phone call to someone. So this is synchronous. So you call someone, the other person responds, and you exchange sentences in talking, well, usually first one person, then the other person, and then the other way around again. So this is what we call synchronous communication. We send something out and we expect a reply back. This is also called rendezvous mode. So a rendezvous is something where obviously you meet. So a sender, when something is sent out, waits for a reply or a reception confirmation by the receiver. And there's also asynchronous message exchange. And this is very similar to when you send letters or emails. So it's more or less fire and forget. So you send something and you hope it arrives, but you don't expect necessarily to get a message back. So the sender does not wait to receive a message back, but obviously the receiver can send a message back, which then also takes place asynchronously. This has the advantage, so asynchronous transfer in general has the advantage that the sender and the receiver can do something else, so they don't have to wait twiddling thumbs until the receiver acknowledges something, but they can do something in between, and then they can be notified whenever a packet with a reply, for example, or an error message arrives. When we talk about communication and message exchange, we also should talk about different modes of communication. So the most simple mode of communication is what we call unicast. So this is one-to-one communication shown on the top right-hand side here. So we have one sender and one receiver. So we have a message exchange from exactly one source to exactly one destination. This is the same as you calling someone on the phone. So you're talking to somebody, and this is exactly a one-to-one relation usually. Then we can have broadcast or one-to-all communication. So in broadcast systems, we have one source, and this source has a message to distribute to all possible destinations. So this is similar when you put a loudspeaker in your window and start blasting music, and all of the people in the range, in hearing range, can hear your music no matter if they want or not. And finally, we have a specialized method of communication, which is called multicast or one-to-many. So here we have a number of receivers, but we only want to send a message to a selected subset of receivers. So some receivers, for those, the message might not be relevant, but for another group, the message might be relevant. So with multicast, we can actually send a message to more than one, but not necessarily all of the receivers here. So we need to identify groups to route the traffic accordingly. And of course, all of this can happen on the network layer. So TCP/IP has provisions for, well, unicast. Unicast is a standard communication method. So we have a sender IP address and a receiver IP address and then port numbers. And then we send a packet from the sender's IP address to the receiver's IP address. That's a unicast mode. We can have broadcast modes. Broadcast modes are notified, if you look at the IP address in binary, that a certain part at the end of the IP address, so the least significant bits, are all ones. So your network address is all ones, so your address inside of the local network, for example, and then you can broadcast the message, for example, to all machines on your local network. So this was used, for example, for sending out messages like, oh, we're going to shut off electricity in the building in 5 minutes, so better turn off your computers. Now the problem is broadcast messages cause lots of traffic if they are broadcast, for example, over the entire internet. So if you would send a broadcast to an IP address which would have the encoding 255, 255, 255, 255, this would imply you want to send a broadcast to the whole internet. Obviously, that's not a good idea. And usually this doesn't work because the routers interconnecting the separate systems, what we call autonomous subsystems on the internet, these routers are configured not to forward any broadcast messages. So a broadcast message is usually only available inside of your own network. Now for an IoT network that might work because you might configure your nodes to run on one certain IP subnet, so you could use broadcast there. Multicast, on the other hand, is a bit more complicated because you have to set up multicast groups. There are protocols for these, and there are special subnets starting with an IP range in IPv4 of 224. But the problem is this really never really caught on. So the protocol support exists, but the software support in very many systems is incomplete or non-existent, and usually it's easily possible to make a large number of mistakes when setting up multicast. So the real problem is, even though we have these communication modes available on the IP level, nobody is going to use anything else compared to than unicast communication, because broadcast is problematic because you don't know how far your broadcast will be propagated, and multicast, as I mentioned, is problematic to set up. So as that is problematic and unreliable, we have to find another solution to implement these communication modes on top of our TCP/IP protocols. So what we do is we actually enable them on application level again. So here you see there's a bit of redundancy because TCP/IP was never intended for setting up modes like this. The interesting thing is, it is so flexible that it's adaptable to be used for it. But of course, there might be a certain amount of overhead involved here, which would not be required if we had another protocol below it. But then again, we would not be the Internet of Things, we would not run on Internet protocols, and we would struggle with different incompatibilities between low-level protocols. So how do we communicate between IoT nodes? As I said, the solution for these deficiencies of the IP protocols is to implement these communication modes, point-to-point, multicast, broadcast, on top of either reliable, so TCP transport level protocols, or unreliable UDP transport level protocols. And for this, an abstraction is used. And one of the most and commonly used abstractions is called a message bus. So we've talked about messages before. We know a message is some information we want to send from a sender to a single or a group of receivers. And the message bus is actually an abstraction that helps us to send messages. So it's not a physical thing. It's just a logical abstraction we create in software. A message bus is defined as a combination of a common data model, a common command set, and a messaging infrastructure to allow different systems to communicate through a shared set of interfaces. And on the message bus, many IoT systems actually implement what we call a pattern, so a certain mode of communication. And this mode of communication actually enables these communication and transportation modes we've seen before. So unicast, broadcast, multicast. And this is done by changing the role, turning it on its head. So in these systems, actually the receivers indicate what they want to receive, and then the senders send out information according to requirements of the receivers. But this is done in a very general way, and this way is called publish subscribe. So this decouples the sending, the publisher, from the receiving or subscriber party. So we say I want to receive information about certain what we call topics later on. So for example, if you want to receive news, you want to receive maybe not all sports news, but only football and basketball news. But you might also be interested in international politics, but maybe not in Icelandic politics, but maybe in Swedish politics, obviously. So a receiver can just send up a number of topics the receiver is interested in, and these are not related to any IP addresses or any multicast or broadcast settings. They're just an abstraction on top, which indicates a semantic categorization of messages. And then for each message that is sent in such a system, not only the message is sent, but also this category is sent along with the message. So when I send a message about a football match result, I send the information back, not only the result between team A and team B, but also this is a football message and not a basketball message and no politics message. So this makes it easy to sort all the information, all the messages we transfer according to these topics. But of course, now we need someone or something in our network to administer these topics. So which topics are available, who has actually subscribed to which topic, which messages need to be forwarded to which clients, and maybe you want to end a subscription, you only want to subscribe to something for a certain amount of time. So this also needs to be handled. And this is done by a component on the network, which is called a broker. So a broker is a node on our IoT network that is used for handling and distributing messages that are sent in such a public subscribe style over a message bus. So this is sitting on top of the transport protocols in the application layer. So what are we going to do with such a broker? Now, we still need a way to format the messages first. So all the machines in our network, all the IoT nodes and the broker have to speak the same protocol in order to interoperate. And one of the most commonly used protocols is called MQTT. MQTT originally had a meaning, this MQ for message queue. It was originally intended by IBM for what they call machine-to-machine communication, but it has seen more general use, especially obviously in the IoT, otherwise we wouldn't talk about it here. So MQTT is a client-server, publish-subscribe messaging transport, and it was formerly just called MQ telemetry transport. And of course, this is standardized in different versions. MQTT had some simple requirements. It should run on very small machines, so it should be able to be implemented in a very simple way. In addition, MQTT messages had different importances or relevances, so you should be able to define something like a quality of service for data delivery in MQTT messages. So some messages are more important than others. It should be lightweight and bandwidth efficient, so it should run over low bandwidth lines like, for example, as we've seen, these low power wide area range networks we've seen in the previous lecture. It should be data agnostic, so you should be able to send any sort of data over MQTT. And it should also enable, persistent connections, so it should have some sort of awareness of a continuous session, so different MQTT messages sent together that belong together in one larger context. And MQTT is essentially fulfilling these requirements by being a very lightweight binary protocol, and this has a very minimal packet overhead because we want to spend most of our bandwidth on the actual data that's to be processed instead of administrative data and other overhead. As I said, it started at IBM as a proprietary protocol and was then released for free, the standard, in 2010, and it became an Oasis standard 4 years later. There are two versions in common use, so the older previous version was MQTT version 3.1.1. This is still commonly used. MQTT 5 is available since 2019 and has a number of improvements over the old version. It's very often used in IoT, but not only. So for example, MQTT is also used in Facebook Messenger. And this reference number 3 here is a link to a blog article by one of the authors working at Facebook implementing it. So how does communication in MQTT work? So the abstraction MQTT uses is a message queue. So we've seen a message bus before, and a message queue can actually be described as a simplified form of a message bus. And in a message queue, two or more processes can exchange information via access to this common message queue on a system. This can be realized over a distributed system over wired over wireless networks. Now, message queues have a certain semantics, and they use the so-called FIFO semantics. FIFO means first in, first out. So this describes the order of messages. So a message that's sent in before another message and at one end of our message queue is guaranteed to come out in the same order in the other end. So the message that was sent first will also be received first. So message queues, compared to a message bus, define a given order of messages, which can make implementing things quite a bit easier because we have a sense of which came before the other. And we'll see something in addition to this in our discussion about data on the IoT in the next lecture in the data part of the course. So a network node in MQTT can have one of several roles. So we can have servers, and this is what was formerly called brokers, and it's in general, you find it also named broker still. So a server or a broker is responsible for distributing messages over the network. So this is something like an abstract version of an internet router which works on an application level instead of an IP level protocol. And then we can have clients, and these clients can have one or two roles. And these roles are, as we said, we have a publish subscribe system. So accordingly, these roles can be a publisher, so a data provider, which sends messages belonging to certain topics. And on the other hand, we can have subscribers or data consumers, which receive messages and indicate which source of messages they want to receive. So the communication in MQTT works as a publish-subscribe pattern. A publisher publishes one or more topics to the MQTT broker. Devices subscribe to a set of topics with the broker, and then messages are sent from the publisher to the broker. The broker has a list of current subscribers to that topic and sends out messages again to these subscribed devices. And here we see an example of a speed meter. So we send out speed information to the broker with the topic, okay, this is speed information, and all the systems that are interested in this information are going to receive a data packet there. So what happens here is we have implemented something similar to our multicast implementation. So we can send data now to selective clients, and these clients identify themselves according to the message type. Now the problem, as you can see here, is we have a certain overhead because each packet for multicast on IP level would only have to be sent out once with this special multicast address. Here, when we send a packet, first it has to be sent from the publisher to the broker, and then the broker has to redistribute it to all of our point-to-point connected clients that have subscribed to this message. So if we have a large number of clients, then the number of packets sent for one message here can multiply significantly compared to if we had real multicast support on IP level. That's the price we have to pay for being able to run over arbitrary configurations of IP networks without additional overhead of configuration on the IP level. So, as I said, MQTT has certain features that go beyond sending messages, and one of these features is that each message has metadata that describes its quality of service. So some messages are more equal than others. Well, that's a citation from Orwell's Animal Farm, obviously. So some messages seem to be more important than others. So for example, if it's just a log message, that might not be that important if it's lost over a congested network. But if it's a control message, then you probably don't want that message to be lost. So how can we ensure or assure that the most important messages are actually preferred in a bandwidth-constrained, unreliable network, for example, a wireless network, in many IoT applications? So what we use is we use this quality of service indicator. So in general, we define quality of service as, a collective of service performances that determine the degree of satisfaction of a user of a service. Quality of service parameters are user-oriented and are described in network-independent terms. Well, that doesn't really help us, right? So if we go to something concrete from this very abstract description of a quality of service, it just means we have different priorities for messages, and these different priorities can have different semantics. So for some messages, when we send them out, our broker should guarantee that they arrive. And for some other messages, we just send them out. If they don't arrive somewhere, we don't care. And then for these messages that are guaranteed to arrive, we again differentiate between modes. So quality of service in MQTT has 3 levels for the transport guarantee. The lowest level, QS0, is this fire and forget. We just send something out and nobody has to take care of that. So if it's not received at the other end, we don't care. And then something can happen on networks like we can send something. It's received by the recipient. The recipient sends a confirmation back to the broker, for example, but this confirmation gets lost. So what happens is that the broker usually runs a timer for each message. And then when a timeout occurs, so a message was sent and no confirmation of reception was received, then the broker tries again for these quality of service packets, which indicate that they have to be received. So what happens then is that the recipient receives the message twice. You might think, well, that's not a big problem, right? Well, imagine you build a vending machine, and this vending machine communicates between the money receptor and the component, like maybe a small robot responsible for handing out the wares in your vending machine. And you send out the money reception sends out the message money received, hand out a bottle of whatever drink. And the confirmation gets lost, but the drink is handed out. And then after a timeout, the broker sends this message again, hand out another bottle, right? And then the customer has two bottles. The customer will be happy, but the operator of the vending machine will not be happy in the long run. So for some messages, it's really important to be received exactly once, not zero times, not more than one time, but exactly once. So this is the highest quality level. So for exactly once messages, we have to ensure that there is exactly one instance of the message arriving. Full stop. Now, the choice of the QoS level should be based on the network environment. So if you know you have a reliable network, you can maybe reduce your requirements. For example, if you have a mobile app uh, that communicates with another system, this could use the QoS 0 whenever it's connected to a reliable wireless connection. So it's fire and forget, because in 99.999% our messages are still going to arrive. But it can fall back to a more strict requirement like QoS1 when connected to a mobile GSM network, for example, where messages can easily get lost. And so, of course, having these QoS levels of 1 and 2 requires storing state in the broker, requires the broker to revisit information and receive confirmations. So this is more overhead, this produces more traffic on the network. So a higher QoS level should usually be avoided if the application doesn't really require it. So here's just again another detailed listing of the three QoS levels here. So fire and forget essentially will not be acknowledged, and it's the fastest way to publish and receive message. The at least one semantic must be acknowledged, otherwise it will be sent again, and the exactly once message. This avoids duplicate packets on the network with the highest overhead. Now, we've talked about QoS. Now we've talked about publish and subscribe in general. So the question is, how do we identify these topics or these subjects that can be published and that can be subscribed to? So in MQTT, clients do not have addresses like an email address. And messages are in turn not sent to specific clients. Of course, these clients do have addresses on the lower level, so they still have an IP address, for example. They still have a port number to communicate, because otherwise the broker won't be able to talk to them. But instead of specifically addressing a single client, because in IoT systems, clients can change, they can run out of battery. We want to maybe add clients on demand when the system is growing without having to reconfigure all the system and reboot and reconfigure the broker. So the idea is really to indicate a set of topics. And a topic can be something like we've said, it's football news, it's baseball news, it's politics news, but maybe only for a certain country and so on. And this can be mapped to IoT topics. So topics are a form of addressing which is not specific to clients, but which is specific to the semantics of the information. And that allows the MQTT clients to share information. And these topics are structured in a hierarchy. So as we've mentioned in real life, we would have news, and under news, we would have sports news, and then we would have football news, but we might only be interested in Champions League's results, but not in the result of the Icelandic Football League, right? So essentially, this forms a hierarchy, like the hierarchy you might be used from a file system. So you have a root file system. In this root file system, you have a directory where all the user data is stored. Inside of this user data, you have your home directory, which has your username, for example. And in this, you have documents and programs and games and pictures and MP3 files and so on. And it works very similar to a path in Unix. So we have separate components which are names, and these components are separated by a slash, and you can line them up, separating each of these components by a slash to form a more complex topic or a topic path. Now, topic names are just strings. To make things easier and more internationally acceptable, they're actually UTF-8 strings. So they are Unicode encoded, so you can not only use ASCII characters, but you can use all sorts of characters like German or Swedish or Norwegian umlauts and special characters. You can use Chinese or Japanese or Cyrillic letters or whatever you can imagine. Or you can even use emojis and whatever is supported in your UTF-8 encoding. The topic names are case sensitive, so an uppercase topic of house is something different than a lowercase house topic. And there is one restriction: they must consist of at least one character to be valid. So a topic of empty string is not a valid topic. Now, the interesting thing about MQTT is that the topic structure is not defined. The only thing that's defined is the topics are UTF-8 strings of at least one character length, and they're separated by a slash. There is no default, with one exception. There's a so-called $sys topic. So this is a specific topic which is reserved for the broker, so the broker can publish information about itself, about its status, about things like number of connected clients, and so on. So the broker is not responsible for creating topics except for sys, but the publishers just announce to the broker, now this is a topic I'd like to talk about, so to publish information about. And also in turn, a client can first say, this is a topic I'm interested in. And even if there's nobody publishing so far, maybe in the future someone will be publishing. So if some messages actually published with this topic in the future, please send it to me. Topics are not permanent, so topics can appear and disappear, which helps to avoid the overload of a broker, because otherwise it would have to be able to remember all the topics that have been published or subscribed to from the startup of the broker. And as you can imagine, we want our systems to run independently, maybe for years at a time if possible. So the broker might run full of, running out of memory when too many public topics are published. So this would maybe enable denial of service attacks. So by making topics non-permanent, this can usually be avoided. So MQTT topics are very lightweight. The client does not need to create a topic specifically before they publish or subscribe to it, and the browser accepts each valid topic without any prior initialization. So we just send a message with a topic, and if this topic is not available so far, we have a new topic at the browser. So we can, for example, subscribe to a single topic, and this single topic is something very specific. For example, we want to be able to get information about the temperature in the living room on the ground floor in my house. So we can create a hierarchy that starts with my home. And my home is probably the top level hierarchy for all the devices that are somehow connected to your home. And then we can split it up. So for example, you have different floors in your home. So you can say we have a second level, a ground floor, a topic level that just is the next level in the hierarchy for all your devices on your ground floor. And then you can say there's different rooms in your house. So there might be a kitchen and a bathroom and a living room. And so you have the different rooms sorted under the different floors. And then you might have different sensors and actuators there. So you might have a temperature sensor, you might have a light sensor, you might have a thermostat, so a heating system or lightings to control. So these topics can be created on demand. And the definition of these topics is something that the person defining the system, building the system, has to do. And of course, you have to invest a bit of work to make it sensible, to make it useful, but also to enable the extensibility of the system. So the important thing is that the slashes, which we print in red here, are the topic level separators. So a slash is the only thing not allowed in a topic name. Now, what happens when we want to subscribe to all the messages happening on the ground floor, for example, but not all messages on the ground floor of, itself, but only the temperature messages for all rooms on the ground floor? Now then we can again use something very similar to what we're used from using file systems on a Unix shell or a DOS command line. We can use what we call wildcards. So wildcard is a special character that stands in for a number of other strings. So wildcard allows matching several different topics at once. This is similar to when you want to delete all text files in a certain directory. You would, in an MS-DOS shell, type del *text, and it would look up all the files ending in .text and then delete them. Now, something very similar is available in MQTT. In MQTT, we have two wildcards. We have a single level wildcard. So this replaces exactly one topic, so exactly one level between two slashes. The example here shows my home / ground floor / plus, which is the wildcard for a single level, / temperature. So this means whenever your topic that's published contains at the beginning my home / ground floor, and at the end it contains temperature and has exactly one level in between, then we match. So we can subscribe to something like this, which avoids subscribing to every single room on the ground floor separately to get its temperature. But you will only get the temperature messages of all the ground floor rooms, but not maybe the light level messages. And then you can also have a multi-level wildcard. So if you're interested in all messages of all devices on the ground floor, you would use the hashmark character, and this can replace one or more topic levels. So you can say my home / ground floor / hashmark, and you would receive all the messages about what's going on the ground floor of your home. But we have one constraint here compared to file system stuff. So this hash mark is only permitted to stand at the end. So it cannot replace several levels of topics in between and then having something at the end. So my home / hash mark / temperature in our example would not be allowed. So here it's only at the end, serving as a catch-all. And that's one constraint that's probably caused by the resource efficiency of the protocol, because that makes it much easier to match. If we would allow a hash mark somewhere arbitrary in between, the amount of scanning and parsing we'd have to do to process these topic strings on the broker would be much higher. So here, remember, we have two wildcards, a plus, which replaces exactly one topic level by arbitrary, and a hash mark. You can also not replace parts of a string in a topic. So it's not allowed to say my home / ground floor / a plus to receive everything that starts with an A. So that's possible on file systems. MQTT makes this a bit more simple. So you need to structure your things accordingly to make this work well for your application. So as I mentioned already, the $sys topic is this reserved special topic. So all topics starting with a $sign are reserved, and they're used by most of the MQTT brokers out there to publish information about the broker itself. They are not part of the subscription when you describe to the very general wildcard. So if you have a topic just of hash mark without any slashes and other topics, this means you would be interested in all topics on the network. That's probably not a good idea in itself because you might be overloaded. Nevertheless, you could do this and still you would not receive the dollar messages here because you'd have to subscribe to them separately because usually you don't need them for your application. For MQTT clients, these are read-only. So a dollar message that is published by an MQTT client is ignored by the broker usually and is not forwarded. So this is something only brokers can actually publish. And the interesting thing is there's, again, no standard for the topic structure, but there's a guideline that most broker implementations seem to follow. And I'll just give some examples here. So, for example, under the topic $sys / broker / clients / connected, as the name says, you get a list of all the connected clients. Again, for disconnected, the total clients, this is a number. You get a number of messages sent, or you can get a number that indicates how long this broker is running already since the last boot up or reboot, so the uptime. Now, when we use MQTT topics, there are some best practices. And one of the best practices first when you use to Unix systems is usually you would want to put a leading slash there, indicating this is the root of my messages. You can do this in MQTT. But in MQTT, this would imply that actually the first part of our topic would be the one to the left of the first slash, and that would be empty. So this leading forward slash is permitted because very many people tend to use it. But this introduces an unnecessary topic level with a zero character, which is essentially empty, which, as we said initially, would not be allowed. So it still works because this is a common mistake that's done, but usually ignore it. So we're reading these things from left to right. There are no things like what we call relative passes in a file system. So we're not at a certain level in our hierarchy and navigate from there on. We always read the whole path from left to right, from start to end. So essentially leave out the initial slash, and that avoids confusion. It's also safe, like in very many file systems, safer not to use spaces in a topic. First, spaces make it much harder to read and debug topics. You might have a line break somewhere in between. There are different space characters, so there's a space or a tab character, and especially in Unicode, you might have additional space characters, which all look the same because it's just a bit of white space on your screen, but of course have different encodings. So using space characters and also using very uncommon UTF characters make your life more difficult. It's probably difficult enough for us if we had to, for example, handle a Chinese or Japanese IoT system where everything's set up using kanji or hiragana or katakana, Chinese or Japanese characters that most of us won't be able to read easily. But we could at least copy and paste them easily if we had them somewhere on the screen, and white space makes more trouble here. Usually, when we have a topic that we want to publish, it's a good idea to embed a unique identifier or a client ID into the topic. And this has the reason that, for example, we have two devices from different vendors that want to publish temperature information, but this temperature information has a different format. So just imagine you buy a European and an American device. One of them publishes temperature information in Celsius, and the other one in Fahrenheit, and just publishes a number. Then your system might get very confused if both of them would just have a topic of something temperature. So embedding a unique identifier, so there's this UUID method where you use a very long, randomly generated 64-bit number, like for file system identifications also, and very many different things, or a client ID. If you give your IDs names or IP numbers or whatever, makes it easier to avoid these mistakes and makes it then more safe to set up your system, even if you have very many different components. As I already mentioned, it's not a good idea to subscribe to just hashmark, because then you might easily get overloaded because you would receive all messages except for the dollar topics from the broker, which might be a bit much for your system. And then it's also a good idea to use specific topics and not general ones. So, for example, you might want to send something to my home ground floor living room temperature and my home ground floor living room brightness for two different sensors about temperature and brightness, instead of sending everything to my home slash ground floor slash living room, for example, and then sending all data of the living room in one big packet or message. So if we take a bit of a closer look, it's always interesting to see how is this efficiency actually generated. So how can we generate small packages? So it's always nice to look at MQTT bytes as they are sent over the network. And MQTT messages are quite simple. So they consist of four parts. The first part, as with all messages or network packages, is a control header. So the control header here consists of 1 byte, and this 1 byte actually has 7 defined bits. The first is a message type, which is a 4-bit number, so we can have 16 different message types. Then we have our QoS level. We've seen we have 3 different QoS levels, 0, 1, 2. Now for encoding 3 different numbers, we need 2 bits, so we have 2 bits QoS level, and we have 1 bit that's called retain. So retain is an indication to the broker that a topic should be retained. As the next information, we have the packet length, and the packet length can be 1 to 4 byte. This is not the length of the data itself that falls, but this is the information about the packet lengths. So this is encoded in an interesting way to save space. Most of the packages will be very short here, or of the messages. So that means if we would spend 4 bytes on encoding a length, usually most 3 of the 4 bytes will be just 0. And so we just waste network bandwidth transmitting zeros. So the packet length is actually in a variable length encoding. And this means that we only use 7 bits of each byte of the 8 bits to encode the actual length. And the 8 bits is what we call the continuation bit. So if we have this continuation bit, which is the most significant bit set, this indicates there's another byte coming containing more length information. And then we add it with least significant byte first. So the first 7 bits indicate the least significant 7 bits of the length. If the most significant bit, bit 8, is 0, then that's all. So we can have messages from 0 to 127 bytes of length. This length can be encoded in just 1 byte of packet length information. If we need something more, so 128, for example, we need to add a byte. So we need, for example, to set this continuation bit and then add the next bit in the next byte. Then we can, if we need another byte, set another continuation bit. And then, of course, the fourth byte always have to have a 0. We cannot send more than, well, 7 bits encoded essentially per byte. So 4 times 7, which is 28. So we can send messages in theory up to 2 to the 28th power, which is 256 megabytes, if I'm not mistaken. This would be quite a long message. So this is definitely sufficient for everything we want to send. But the interesting thing here is due to this variable length encoding, we're not spending more bandwidth than required for short messages. So here's an example. If we want to transmit a packet of 257 bytes, then we need to encode the length as 2 bytes, and these 2 bytes would be 0x81. So this would indicate as we see on the right-hand side, a binary 1 plus a continuation bit, and then the next 7 bits would be indicate that this is 256. So this would be bits 8, 9, 10, and so on. So this is 1 to the power times 2 to the power of 0 plus 2 times 2 to the power of 7, or 257. And as I said, the continuation bit of 0 indicates the packet length information ends. Then we can have a variable length header before the payload. This variable length header, its size depends on the type of the message. So the type of the message are the first 4 bits of the first byte, so the control header here. So we have to encode this information in our clients so we know how long this variable length header is for each message type. And finally, of course, we have a payload, so the data itself that should be sent. So we can see the structure here on the lower right-hand side and the order in which something appears. When we send information, we can have possible formats of a fixed header. So this contains a control field and a length. And as I said, we have different message types. For example, this would be a message with a type of CONAC, so a connection, acknowledge message that's sent from a client to a broker. We can have a fixed header plus a variable header here. So this would be a publish acknowledge. For this, we would need something like a topic. And then we can also have a payload in addition, which would be a connect message. So this protocol is very simple. It's easy to implement also on a small microcontroller. And we just give some examples here for the structure of these messages. We can't go into all of the details in the available time. So please refer to the standard for additional information on this. Of course, usually you won't need this specific information. You would need it if you want to implement your own MQTT middleware, but it's always good to know stuff like that when you want to debug messages. So, for example, when you have a debugging tool for your network like Wireshark, you could have a packet capture, and then you could have this packet capture decoded when you know this exact structure we described here. Of course, since MQTT is very ubiquitous, now decoders for these formats already exist, so you don't have to do all the mangling of the hexadecimal bytes yourself, though it can be fun at first. So we have different message types. For example, we have messages indicating connections requests. So on the right-hand side, we have a timeline of communication between a broker and two clients. And for example, the first message that's sent from client A is a connect message. So the client A wants to connect to the broker, and then the broker sends a connection acknowledge message back. So now you're connected. And as soon as you're connected, you can, for example, publish a message here or subscribe something. So client A, as its next action says, it wants to subscribe to a topic temperature / roof. And then we see on the right-hand side, before the subscription, client B has already published a message temperature / roof with the information it's 25 degrees centigrade and a flag that says retain. So this message, even though the subscription request comes after the send request, after the publish request, this message was retained at the broker. So this will still be available even though the subscription came after the publication of that topic here. So this message is immediately sent to the client A after its subscription request because it was marked as retained. And then maybe client A wants to publish something. So as we've seen, clients are not exclusively publishers or subscribers. They can have both roles. So for example, our client A wants to publish another temperature, its own on the floor, which is 20 degrees. This is not subscribed to by anyone. Well, the broker probably, because it doesn't have a retain flag, probably throws it away. And then we have another publish message from client B, which has another roof temperature. And this is again received by client A, which subscribed to this type of messages. And client A can then disconnect if it has received all the messages it wants. So this is a very basic communication. There are additional ones which I would ask you to look up in the standard if you're interested. So MQTT brokers exist in many forms. There are commercial solutions, there are open source solutions, and one commonly used open source solution is called Mosquitto. Mosquitto is an open source project supported by the Eclipse Foundation. It's written in C, so it can run on most machines that have a C compiler available, from small AVR controllers like in Arduinos to a Raspberry Pi or even a regular PC, and it can be compiled on Unix, Linux, Windows systems, and probably on a large number of embedded systems too. It's relatively simple to install and test. You can have command line tools to work with it, so you can easily debug things. It has low resource use, so you can, for example, run the broker on a Raspberry Pi with Linux as a service in the background. And there's TCP ports standardized, so the Mosquitto MQTT communicates over TCP, and the two ports 1883 and 8883 are reserved for MQTT broker use. And then you can test them out. When you have installed it, you can use a command line tool to publish a message belonging to a topic. So there's a tool provided along with the Mosquitto server called Mosquitto Pub, which gets a reception address because, well, we have to indicate it somehow. So we want to send it to the broker at address 192.168.0.1, which is indicated by the -h parameter. And then we want to send a message called on, indicated by -m, with the topic indicated by -t, house / light bulb. So obviously we want to switch a light bulb and the house on. You can also send optional information, like you can do things password protected, so you can require users and passwords. We can have the retain flag. We can send client names and even do encryption of messages using SSL protocols. And on the other hand, you can also monitor a topic from the command line. So you have another tool called Mosquitto Sub for subscribe. Again, you tell it what address the broker has, and then you can say, for example, you want to subscribe to the topic with -t house / hashmark, so to all the messages about the house coming in that's been published. And there you can also send options like, I only want to have the first n messages, I want to be more verbose, so get more information, and also want to have a certain quality of service levels. So there's a lot of documentation on Mosquitto out there. It's provided in typical Unix style man pages, And if you have Mosquito, you can easily, if you have a Raspberry Pi, for example, build your own minimal broker, and then you could attach a different number of of IoT clients using, for example, a wireless network. Now, amazingly, MQTT is relatively lightweight, but people wanted even more lightweight versions. So for very small sensor networks, even this minimal processing that we provide with MQTT is quite a bit of overhead. For example, long topic strings might just exceed the capabilities or the RAM in small microcontrollers. So in very small microcontrollers like AVRs, you might only have a kilobyte or two of memory. And if you would have to spend like 256 bytes for a long buffer for a topic, well, then there's not much memory left for your application, as you can imagine. So the general difference of MQTT-SN for sensor networks, so this indicates it's for the small nodes at the edge of your network. The difference to regular MQTT is that there's a reduced size of the message payload, and we don't have permanent connection requirements. So TCP itself, compared to unreliable transport UDP, also requires much more overhead in your TCP stack. So UDP is much simpler to implement, requires less resources and also less RAM. So MQTT-SN doesn't require a permanent socket connection because it's using UDP and not TCP as a transport protocol. And just some details here. So the connect message here is split into 3 messages where 2 are optional. So this saves network bandwidth, and especially topics are replaced or have alternative versions. So you can have topic IDs instead of topic names, which are just 4-byte integers. You can also have short topic names, which just consist of 2 characters. And you can also have predefined topics on such an MQTT-SN network, which don't require registration. So they're just something which make it easier and simpler to set up things without that much overhead. So it's just making it a bit simpler again. And this is very useful when you have low bandwidths and low processing and memory available. So the interesting thing in MQTT-SN is that this adds a new component, which is called a gateway. And this gateway can then provide a transparent connection to a broker. But the important other thing is the gateway can also aggregate messages. So if we have multiple MQTT-SN clients, we can actually have a gateway somewhere that just puts all these messages together and sends them to the broker at once. And we also have a discovery process. So for MQTT, we've seen we had to specify an IP address. Here we have a discovery process that lets client discover a gateway, and then only the gateway has to know where the broker is available, how to talk to it. And we had a method for offline keep alive. So this means a client can go to sleep, and when it wakes up because some event came in, some interrupt or whatever, then the client wakes up and can just connect again. So this is a bit of the difference, but in general, the idea behind MQTT-SN is very similar to MQTT. It's scaled down, and you can also be interoperable using a gateway from an MQTT-SN system to a regular MQTT browser, and then the gateway is responsible for translating, for example, complex topics to simple topics, and so on. Now, as I said, the nice thing about it is there are more than one standard out there. So there's competing standards for messaging middleware for the IoT. So one of the recently discussed other ones is called ZeroMQ. So ZeroMQ is described as a middleware aimed at the use in distributed and concurrent applications. So this sounds very appropriate for IoT. ZeroMQ provides a message queue, but unlike message-oriented middleware that we've seen before, a ZeroMQ system can run without a dedicated broker, and that's why the zero is there part of the name. So that makes things a bit easier because you don't have to set up a central broker. And in turn, of course, if you have a central broker, this is a single point of failure. So if the central broker fails, well, then the rest of your devices won't be able to communicate anymore. So ZeroMQ makes this easier. The API of ZeroMQ is designed to be very familiar to people who programmed the internet applications before. So it's designed to resemble the most commonly used interface for network programming, which is called Berkeley sockets. This is available in Unix, but also in Windows, for example. And this has several communication patterns, like a request-reply pattern, so you can connect a set of client to a set of services. This functions like a remote procedure call, or RPC. We can have a publish-subscribe pattern, as we've seen before. We can also have a push-pull pattern, so a pipeline between two nodes on the ZeroMQ network, like a Unix pipeline, where you put in stuff on one end and it comes out on the other hand. But this can also have multiple steps and loops and repetitions, and it can also have a fan out and fan in pattern, which means you can have several things writing to one end of the pipeline and several clients receiving messages at the other end of the pipeline. And you can also have exclusive pairing, so this would be a one-to-one connection. So I'm not going into more details. ZeroMQ has differences. If you're interested, we've given reference 13 for you to learn more about this. So the big problem is really when you buy different devices from different vendors, you want them to be interoperable on the IoT network. So we have seen three standards, MQTT, MQTT-SN, and ZeroMQ. We've already seen there's a gateway between MQTT and MQTT-SN. But there are a number of other middleware standards for IoT applications out there. Another one that's pretty common is AMQP. And what we need is we need to bridge these different concepts and approaches. And this is sometimes difficult because the semantics between the different systems are quite different. So for example, AMQP does not have the topology of a hierarchical organization of topics or a topic graph that we've seen in MQTT. It also does not have inherent subscribe and unsubscribe functionality. So we've seen typical MQTT messages in green on the left, and the more complex MAMQP messages on the right. So again, we need a gateway also here to translate and match these concepts. And of course, I couldn't avoid putting the obvious XKCD comic on this on the top hand side. So you start with a situation where you have 14 competing standards, and you have the great idea, let's create a standard that encompasses all these standards. So you end up with 15 competing standards because you won't get everyone to agree on your new standard. That's life. That's the interesting thing about the internet, that it's agnostic to these things. This is just happening above the transport level, so the internet doesn't really care. You're allowed to transport on the internet whatever you want, as long as you keep to the TCP and IP standards, for example, for TCP connections, and everything else can be defined at will. That's why we have new protocols. That's why Tim Berners-Lee at CERN could invent the World Wide Web, which had a brand new protocol without registering it first anywhere, without getting permission, just putting a server on the network, and nobody cares what's inside of your data packets. That's a nice thing, but of course here it also causes lots of trouble, because even though there is a central agency responsible for setting internet standards, the Internet Engineering Task Force, IETF, well, it cannot forbid packets of arbitrary content to be sent over the internet. So essentially, IETF can only propose things like the RFC, the request for comments, setting standards, but above the TCP level or above the IP level, you're on your own. And larger companies like some of the FAANG companies like Google and Facebook have already tried to define their own transport standards as a replacement for TCP, for example, to get faster transport for web pages. So things like these can happen, but they fragment the whole market, the whole internet even more. So a good question is if this is a useful approach. Well, this is not for us to decide, but something you should be aware of. So MQTT is very common, but it's not the only thing out there. So if you go out and buy a device, take care of which protocols are supported. And if you create a device, you need to indicate, for example, if you have a certain market, you need to figure out what's the common protocol in that market. And then it's probably a good idea to support this protocol, or maybe even a number of different protocols if you have enough resources available. So what have we learned today? We've seen protocols for the IoT have to build their functionality on top of TCP/IP because we want something like multicast and broadcast functionality, which are not easy or not reliable on TCP/IP level. So what we are trying to build, because IoT devices have limited resources, we try to build lightweight abstractions that are on top of TCP/IP. And we've seen these abstractions being used as message queues and message buses. We've seen the publish subscribe pattern. That's a very common pattern that avoids storing address information by just having topics. That makes it easier to dynamically reconfigure things on the fly, to add and remove nodes. But for this, we need a broker as a central component to handle this high-level data exchange, and we might have packet duplication, so a higher network bandwidth use compared to if we would have a solution on IP level for this. And we've seen different protocols. We've seen a number of details on MQTT, which is commonly used. We've seen a scaled down version, MQTT-SN. We've seen at least that there are other protocols like 0MQ and AQMP that exists. Some of them are actually proprietary, so you don't get free access to the standards. For some of them, you at least get a free implementation, but not a standard, so you have to read the standard from the implementation. And one of the biggest challenges of IoT systems, especially in future, if IoT systems proliferate more and more, will be to enable interoperability between all these different protocols, to get all these different devices really to talk together without having to manually configure too many things. So that's all for today. As always, here's a list of references, which contains a large number of web pages this time and not that many papers. Of course, we have standards like specifications here and a lot of blog articles. So if you want to get your hands dirty and set up something using MQTT, I think you will find a number of interesting links there. So thanks for listening. This was the last part of the infrastructure part, and in the next part of the course, we'll continue with data on the IoT. Have a good time. Until next time. Bye.